Have you ever wondered what lies at the heart of your favorite electronic device? From your morning coffee maker to the smartphone you're likely holding right now, there's a common thread that ties all these devices together. It's a marvel of modern technology known as a printed circuit board, or PCB for short. In essence, a PCB is a thin board made of fiberglass, composite epoxy, or other laminate material. It's like the city plan for your device, a roadmap for electrons to travel, guiding them where they need to go. These electrons power your device, allowing it to perform its intended function. PCBs are the unsung heroes of our digital age, the silent powerhouses that drive our world of electronics. They're the heart that keeps your device alive, pulsing with electricity and humming with life. So how do these intricate pieces of technology come into existence? Let's unravel the mystery. The creation of a PCB starts with a blueprint. A blueprint, in essence, is a detailed plan or map that guides the creation of something complex. For a printed circuit board or PCB, this blueprint is the schematic layout. The design process of PCBs is a meticulous one, largely because the functionality of the electronics it's going to power hinges on it. The first step begins with software, specifically computer-aided design or CAD software. This incredible tool allows engineers to meticulously plot out the paths of electrical current, place components, and ensure that everything is in its right place. Creating a PCB is a bit like orchestrating a symphony. Each component or instrument has its part to play, and it's the conductor or the engineer's job to make sure they all work together in harmony. The schematic layout is essentially the sheet music for this symphony. It's a visual representation of how the different components of the PCB will interact with each other. Once the schematic layout is complete, the design isn't quite ready for manufacturing yet. The next step is to put the design through its paces using simulation software. This is a critical step in the process, as it allows engineers to test the layout under different conditions and make sure it functions as intended. It's a bit like a dress rehearsal before the main performance. The simulation software can detect issues like short circuits, component failures, and other potential problems. If any issues are detected, the design can be tweaked and retested until it's just right. This iterative process can take time, but it's crucial to ensure the final product is reliable and efficient. Once the design has been thoroughly tested and all potential kinks have been ironed out, it's time to move on to the manufacturing stage. But remember, the journey of a PCB is far from over. The real test lies in how well it performs in the real world, under real-world conditions. Once the design is foolproof, it's time to bring our blueprint to life. With a solid design in hand, it's time to start the physical creation of our PCB. Our journey into the tangible realm begins with the transfer of our meticulously crafted design onto a copper board. This step, often referred to as printing, doesn't involve any ink. Instead, we use a specialized film that adheres to the copper surface, replicating our design. It's like a blueprint for the copper to follow, guiding it towards its ultimate form. Once our design is firmly imprinted on the copper board, we move into the etching phase. Etching is akin to sculpting, but instead of adding material, we're taking it away. Here, we submerge the board in a chemical bath that eats away at the exposed copper. But don't worry, our design, protected by the film, remains intact. This process, fascinating as it is, results in a copper board that mirrors our initial design. Now it's time for the drilling process. This is where we create holes for component placement. The board is placed on a drilling machine, and using our design as a guide, precise holes are drilled. It's like a connect-the-dots game, but instead of creating a picture, we're creating pathways for electrical currents. This drilling process is a delicate dance of precision and control. Each hole must be perfectly aligned with its corresponding component on the design. Even a minuscule misalignment can lead to a faulty board, and we certainly don't want that. Throughout this process, we maintain an unwavering commitment to precision. This commitment ensures that each PCB is a faithful representation of its design, ready to bring our electronic dreams to life. But our journey doesn't end here. Now that we have our PCB, it's time for the next step, adding the components. This is where our board starts to take on a life of its own, transforming from a mere piece of copper into the heart of an electronic device. Now, with our board ready, it's time to add the components. The next step in our PCB journey is the placement of components. This is where our circuit board starts to look a lot more like the heart of an electronic device we're all familiar with. It begins with the careful placement of various electronic components on the board. Resistors, capacitors, diodes, transistors, and integrated circuits, among others, are placed on the board in precise positions. This isn't a random process. It's all according to the design blueprint we discussed earlier. Now, these components aren't just thrown onto the board and left to sit there. They need to be secured, and that's where soldering comes in. Soldering is a process where a metal or alloy, known as solder, is melted to create a conductive join between electronic components and the PCB. You can think of soldering like gluing, but instead of regular glue, we use a special metal alloy that not only secures components to the board, it also establishes electrical connections. Simply put, it's the solder that allows electricity to flow between the various components on the board, bringing our electronic device to life. There are different methods of soldering, with the most common being wave soldering and reflow soldering. Wave soldering is a large-scale soldering process where the PCB is passed over a pan of molten solder. The solder sticks to the areas where it's needed and the excess is shaken off. On the other hand, reflow soldering involves applying a paste of solder and flux to the areas where components will be placed. The board is then heated in an oven, causing the solder to melt and form the necessary electrical connections. So after the placement of components and soldering, our PCB starts to resemble the heart of an electronic device, with all its components secured and ready to work in concert. With all components in place, our PCB is almost ready. But there's one more step. No PCB is complete without thorough testing and quality control. Now that we've built our PCB, it's time to ensure that it performs to the highest standards. This is where testing and quality control come into play, and they can make or break the success of our final product. The first step in this process is a visual inspection. Specialists meticulously examine the PCB for any visible anomalies or defects such as solder bridges, incorrect components, or misaligned parts. But the human eye can only see so much, and that's where technology steps in. Next is the automated optical inspection, or AOI. This high-tech process uses cameras and software to scan the PCB for any faults that might have been missed during the visual inspection. It checks for component presence, polarity, and offset, as well as solder paste volume and position. AOI is crucial because it can detect issues that are virtually invisible to the naked eye. But even after passing the AOI, we're not done yet. The PCB must also undergo functional tests. These tests involve powering up the PCB and running it through its paces to ensure that it works as intended. They check the integrity of the circuits, the performance of the components, and the overall functionality of the board. Testing and quality control are pivotal in making sure that our PCB is reliable and effective. They ensure that the PCB doesn't just look good, but works well too. After passing rigorous testing, our PCB is finally ready to be the heart of an electronic device. We've traveled through the intricate journey of PCB fabrication, a journey that begins with a concept, a blueprint, a design that outlines the path for electrons to follow, bringing life to our beloved devices. This blueprint is then transformed into a physical reality, a tangible board of copper and fiberglass, meticulously etched and drilled to perfection. This is just the beginning. Each tiny component, each resistor, capacitor, and chip is carefully placed and soldered onto the board, creating a miniature city of electronic components. This city, however, is not complete without its citizens, the electrons. They flow through the carefully laid out paths, bringing functionality and purpose to the board. But it doesn't stop there. Each board is put through rigorous testing and quality control, ensuring that every connection is secure, every component is functioning, and every signal is clear from interference. Only then is a PCB ready to be the heart of an electronic device, ready to pulse with the rhythm of electricity. And let's not forget the touch of gold, not only for aesthetics, but for its superior conductivity and resistance to corrosion, ensuring the longevity of the device. So the next time you use an electronic device, remember the fascinating journey of its heart, the PCB.